Our first speaker is Kaushik Mitra from the Department of Geosciences, and he will be presenting Early Mars, Red and Dead, or Green and Clean.
Mars is a dead, red, and a desolate world. It's not a very good place if you want to go for a vacation. But why do we care about Mars? We do because Mars can tell us about Earth. While Earth has very little information about the first few billion years of its formation due to plate tectonics, Mars, on the other hand, has all these billion-year-old rocks everywhere on its surface. So, if we want to learn about early Earth and how life evolved on early Earth, we need to know about Mars. Now, we know a lot about the surface of Mars, and it's red from a very long time. The rovers that have been there have confirmed that we have red-colored minerals, which are basically rust-like compounds. Mars was also blue or had liquid water on its surface. As you can see, flowing liquid water carved out channels on the surface of Mars and made these really beautiful river valleys and outflow channels. However, for a substantial amount of time, the liquid water that was there on the surface was really acidic, and it looked something hideous like this. The next question is, was Mars green? In other words, did Mars have oxygen in its atmosphere? Well, the present atmosphere of Mars do not have oxygen at all, or in trace amounts. What might have happened? Did Mars have oxygen early in its atmosphere? Well, to get to that question, let's think about Mars. Let's think about Earth. Earth's manganese oxide were formed when Earth's early atmosphere had oxygen in them. That means manganese oxides can tell whether you had oxygen in its early atmosphere. Now, there's an asterisk in there that tells that there is a catch. There might be something very specific about this kind of correlation. We have found manganese oxides on the surface of Mars, and lo and behold, the Mars community started to think like this. If Mars had manganese oxides, it must say that it had oxygen in its early atmosphere. Now, there is a problem here. We saw that the waters on Mars were different than the waters that we have on Earth. The waters were really acidic. Now, what I am going to test is whether oxygen can actually produce these manganese oxides in Mars-like fluids. What I did is going to show here is the time taken by oxygen to produce manganese oxides in Mars-like fluids. In the y-axis, we have time that is required to oxidize manganese in years, and in the x-axis, we have the pH of those fluids. This blue shaded region denotes a time period in which liquid water was stable on the surface of Mars. And the red region in here shows the pH range in which the pH range of the Mars liquid waters that were there. The shaded green region in here, that means the shaded green region is the area of interest, the Mars relevant conditions. The results that I had from my experiments and simulations showed that none of these actually fell in that green region. That means oxygen was not able to form the manganese oxides in Mars-relevant fluids in the desired time limit. But we do see manganese oxides. But how did they form? The answer lies in another interesting set of compounds that we have on Mars, which are called reactive chlorine and bromine species. They were able to produce the manganese oxides on Mars in way faster timescales and really in the Mars relevant fluids. Now, what I have proposed, the manganese oxides do not say that there was oxygen, but they say there is a very complicated and ghastly looking halogen cycle that is happening. There's a huge amount of chlorine and bromine that is happening here. What I want to conclude is Mars was never green. It never had it never had oxygen in its atmosphere. But I will also say that life always finds a way. Mars might have life, but it might be very special to the red planet. And we should never stop exploring, because truth is always stranger than fiction. Thank you.